think everybody's here. Yeah. So yeah, I still didn't find out. I forgot to ask which of the bounce back criteria was the best. But as I said, this is for you guys to implement in your Christmas break. So I have a couple of videos showing my code for this lattice gas cellular autonoma. And okay, before we do that, I just remembered something. So if you read the book, what you're going to see is that he uses this notation. D2Q7, for example. And I took me a very long time to even ask what that meant. But the way it works is this is dimensions. So we're in 2 dimensions. And Q, if you ever talk to a physicist, he's going to talk about Q1, Q2, Q3, Q4. I don't know why they have so many dimensions, but this is basically the spatial directions. Okay, so this is directions. And why is it 7 and not 6 when I have a hexagonal grid? Exactly. So in the Lattice Boltzmann model that Ifan made, and you will be supplied his code because he's giving it out for free. I think he should take some money for it, but it's fine. He uses something called D2Q9. So he has a Cartesian grid where you can have directions northwest, northeast, north, east, west. So you have all the directions with 45-degree interval. And that's good because then you don't have to shift your coordinate system. Nice. But then you also have to handle the fact that you have a non-unit velocity. So the velocity of the particles moving this direction here, they're going to be, so if we have a unit velocity here and we have a unit velocity here, then we're going to have a square root of 2 root velocity there. So that's another problem. It's not very hard. But okay, back to this little animation that I made. So I have a closed system around here. This is my boundary. And then inside it's empty where it's dark. And I'm basically, you can think of the more yellow it is, the more particles it has. Okay? So it's a way to display the energy of the system. And when I initially did this, I was trying to draw the little arrows, doing the quiver and all this. It was really slow. But then I came back after Easter, and he and Nifan had a meeting, and he said, "Dummy, why are you doing this stuff? You should be plotting the energy. That's the right way to do it." And I agreed. And so you can see the density type. It's like the energy or the density, it's however you want to see it, the number of particles. So I start here with a cluster of particles with random directions. And then we're going to see what's going to happen, right? If it was a gas, we would expect it to, spread out and then after a while reach equilibrium, where you have the same amount of particles on the right, on the left. Let's see what happens. It's a bit slow, but we have time. See, it's hitting the wall, going around, and then slowly but surely the particles are leaking through to the other side. And so what I was saying that I was having trouble with is that if you add up all the values in here, that's the mass, more or less, because you have unit velocities. So I was having trouble with the fact that my boundaries were creating energy or mass, and that my collisions were creating mass for some reason. So I was, to make sure that this worked, a good thing to do is to plot the sum of the particles as a function of time to make sure that it's a constant. Okay, so here we have something that looks like it's reached equilibrium. This goes on for a long time. But you see, it looks sort of gas-like. I think that's pretty interesting that we can even get a gas-like system using a very simple model. it's not easy to calculate. It takes, you have to make this long list, and it's a bit slow and all this stuff. But the principle is conservation of momentum and conservation of energy by gridding and having a very simple stream and collision system. One thing to point out is that you can see that along my boundary, I have, it looks like there are particles on my boundary or in my boundary, and that's because that's how it is. I defined my bounce back criteria like this. So post collision, the particle is actually in the boundary. That's just something you need to be aware of. So yeah, and then here I have a system where I have a bounce back boundary on top and below. And what I'm going to do is I'm going to create random velocities here or particles coming from the left. Okay. And what I'm hoping to simulate is something like fluid flow around an obstruction, just a line. And at the end of the Boltzmann part of the lectures or whatever, then we do the same experiment. Ethan did the same experiment in his model, and it looks a lot better. But for now, let's just see what very simple billiard ball model does. So we have the particles coming in. So nice. Hits the boundary. So initially, it looks like it's just, you only have the particles going out like that. It's not very physical, but you see a slight increase in the number of particles along this direction here. And these are going to go and bounce back up here. You get this, you get some particle movement behind the plate. But what you see is that here there's going to be fewer particles, and then there's more here. And for some reason, there's less back there. That'll fill up. So you can see this code is a recording that I took on my screen. You can see how slow this is being plotted while simulating. So it's pretty not efficient. Okay. Did it make sense kind of how things were moving? And it's a bit cool to see that you can actually get a gas-like behavior from a model which is having unit masses, unit velocities in only 6 directions. And if I'm being smarter than I am, he actually set up an experiment. So in this case, the flow is coming from the right. And this is taken at a time, at some time step. And this is taken at a later time step. So the flow has been allowed to basically flow for a while. And what you see is that the front of the flow, so basically the density of particles is distributed differently based on the basically the width of the pipes that the fluid is flowing through. So the black here is I've just marked over. That's the bounce back points. So those have solid, the S is equal to 1 in all of these points. And what you see here, the fluid barely gets anywhere because you only have 2 pixels to go long. So if you're hitting the wall, you're going back, and then you're basically restricting the flow. Here it's moving along, but you see you have less particles here than you have in this case and this case. But these two are a little bit harder to kind of see the difference in. So you're actually getting the effect of reducing your pipe restricts your flow, which is interesting to see. And I thought it was a very neat illustration of how you can quantitatively say something based on the model. And when we get into the Boltzmann part of this simulation, I'm going to tell a little bit about the history of Boltzmann himself. It's kind of a tragic story, but if he had had these simulations when he was alive, he would most likely be, awarded whatever prize they had back then, and he would not have killed himself because everybody believed that his theory was wrong. Gas acting like particles, that's crazy. And so the significance of us being able to recreate something like this is a little bit bigger than I originally thought when I was doing it. Okay, so now you guys can choose. Either we start talking about like an introduction to the Boltzmann equation and kind of statistical mechanics, and then going into the Lattice Boltzmann modeling, or I can pull up my old code from the lattice gas simulation, and then we can. What time is it now? Maybe end a little bit early, or take some questions at the end, or something like that. So it's up to you guys whether or not you want to look at the code or continue on with the theory. Anybody have a preference? Continue? And we can look at the code later. Okay, so I think I'll just talk about the concepts first of a bit of statistical mechanics and the history of Ludwig Boltzmann. So the idea is basically that we're moving from zeros and ones to distributions. Okay? So we need to have a concept of the distribution function and what it means and so on. So it's going to start a little bit abstract and get better, so just don't freak out quite yet. So imagine that we have some phase space. That means that we're plotting a direction, x, say, and a momentum, p. Okay, so we're plotting we have a system of millions of particles, and we're taking those particles at a certain x with a certain momentum p. Okay? That's phase space. That's how we do it. That's, physicists, they love phase space because it tells you all these crazy stuff. If you heard about Heisenberg's uncertainty principle, they always talk about P and X and T and E. So what we do is we basically grid up different sections in phase space. And then we look at the particles here at a certain x and p. And we say that those particles, they have some distribution function, f, of x. So that's going to be a vector, x, y, and z. And momentum p, that's the momentum in the x direction, the momentum in the y direction, momentum in the z direction, and the time. Okay? So this distribution function is going to be a value between 0 and 1. Okay? If we've normalized it. Another way of thinking about it is saying that if we integrate this over all the x and momentum, then we're going to get the number of particles. But then this wouldn't be a probability distribution. Then it would be something else. So we normalize it by dividing by the number of particles. Okay, so just think about it as a distribution of particles with a certain position and a certain momentum at a certain time. Okay? So we have some of these particles are going to move from this position to this position here. Okay? So we say that the particles are in motion. They're changing. They're being forced into another position by some external force. And this is going to be the streaming process. So we're going to say that the distribution function at the neighboring point in phase space, so x plus delta x, and momentum plus the change in momentum, and then t plus delta t, we just say that that's equal to the distribution in the previous direction. Okay? So it's like saying that your particles are here, kind of, and then they're forced in some direction, so they go to the next region of phase space. So we just say it's equal to this. And if anybody's wondering, when I do the double lines here, it means that it's a vector quantity, just to be, because I can't do bold in writing. So, okay. So this is our streaming. Okay. It's a bit abstract, but let's just carry on. So if we're looking here, we get the contribution from this. But along the way, we're going to have some collisions, right? Because that's what gases and liquids do. They collide with each other. And because of the collisions, there are some of these particles which are going to move to a different region in phase space. Okay, they're not going to get there. So we're going to have to subtract by some gamma, some value, and we're going to say that it's we're implying that these are the particles that didn't get there. But we're also going to have collisions in other regions of phase space, so we're also going to get some contribution that we didn't expect. Okay? So we're going to have to add some quantity gamma, which is going to be the positive contribution. Okay? Don't correct me. I know it's a bit simplified, but and this collection of additional and subtracted particles, it's going to be our collisions. Okay? So we have a distribution function, and we're saying that the distribution function at the neighboring point, it's going to be what's forced into that neighbor. But then some of them are not going to get there because of collisions, and we're going to get some extra contribution because of external collisions. Okay. Now we're almost at the Boltzmann equation. Very simplified derivation. But this here, we can expand by using a Taylor approximation or Taylor expansion. Okay, and you guys remember? I'm sure he's gone through it. But when you have multivariable Taylor expansion, just reminder. So if you have different letter h of some vector, and we want to find its neighboring point, the way we do that is by taking at some point h, and then we do plus gradient of h, right? That's the first term, the first two terms. And then this is going to be the gradient in the x direction. And what I mean by that is just del x, del y, and del z. But here, we have a momentum direction as well and a time direction. Okay? So let's see. Yeah, I'm missing the differences, right? So they're going to be messing a bit up. The dAx and the dP and dt. Yeah, but because now we want to do the Taylor expansion of this. So we get f of x, t, and t, right? And then we're going to get plus, and we're going to get yeah, I know where I forgot here. Don't worry about it. We're going to get the gradient for the x directions of f. We're going to get the gradients in the p directions for f. And then we're going to get del f, del t. And this should be del x. This should be del t. This should be dt. Right? And so this is going to be equal to x p t. Then this, I'm just going to combine the collision terms into some sort of a phi. Okay? We see that this cancels out with this. How close am I? Shh. Somewhat close. So here we have f, sorry, del p, and then del f. Is equal to the collision term. And this is a way to formalize the Boltzmann equation. It's a bit wrong because it's missing some stuff, but don't worry about it. The main part that I wanted to get through here is this equation here. The streaming part is just saying that we assume that there are no collisions when the particles go from the one region to the other region. And then we add the collisions on afterwards. That's our approximation. Okay? And this, this was all developed, and it's pretty heavy-duty math, and it's statistical mechanics, and it's, Boltzmann was doing this back in the 1800s, yes? And nobody believed him, because back at that time, people thought that, well, particles are moving through the ether, right? And they just assumed that, all this stuff that's happening has to react with the ether in some way. And what Boltzmann said was basically, no. There's no ether. There's nothing between the two particles. The two particles are just here and here. And then most of the time, they go past each other and have no effect on each other. And in some cases, they collide and they change direction. And this was radical back in the time of Boltzmann. And when he wrote his book, Lectures on Kinetic Gas Theory, every assumption he made is followed by a long description of why that assumption is okay or valid. And that's not very common to do, especially not nowadays. If you were going to write a book on the Boltzmann equation or kinetic gas theory, he would just, this is your assumption, done with it. But the reason why he explains it in such detail is because he knew that every single person who read it was going to be extremely critical of his theory. Well, almost everybody. And it was so severe that he thought that all of this work, remember, he made up the concept of entropy, or formalized the concept of entropy. And he had this great theory that people were so critical that he felt like it was all for nothing. And it, among other things, that is believed to be the reason that he took his own life. And only a couple of years afterwards, I think it was like 5 or 6 years after he killed himself, everybody agreed on it. And it was the established theory. And it just shows, if he had lived a couple of years longer, then he would have probably been able to figure out even more stuff. Because he had this incredible insight. And it was like, it took 100 years before he wrote down his formulation of the Boltzmann equation, before anybody could make an approximation that was even close to relevant for calculations or for understanding. So, yeah, just a bit on the history. I think it's fascinating, the whole Boltzmann, this stuff. But this is the important part. We have streaming and collisions. And this should trigger some of you to think back on our lattice gas model and say, well, yeah, there we had the particles moved, the information moved from the one node to the next node, and then we had a collision, a list that told us the output, and then they moved to another node. So maybe we can use distribution functions and some ideas from statistical mechanics to create a similar type of simulation as the lattice gas cellular autonoma. So take this away. Now we're not going to look at phase space anymore. Now we're going to look at actual space. So we have X and Y. We grid it up into some grid. And then we say that in that point, we have a distribution of particles moving in each direction. Okay? So we say we let the particles flow there, 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 so on. Those are all the directions we let the particle move in. But there's a distribution of particles moving in this direction, in this direction, in that direction. So the value is going to be F and not 0 or 1. And F, it can be anything between 0 and 1. And that's a key difference. So we basically get something like this, but we say that we have a distribution in each direction. Like this, including the 0th direction, so the non-moving. And then we get this thing here. And what we can do is we can, for simplicity's sake, we can unfold it. So we just make a plot of the distributions. So F, A, function of A. So as a function of the direction, maybe we have, this distribution for the points that have no velocity or no direction. And then we get, something like this. Okay? It's not really important what this looks like. The only thing that's important is that it's just some values between 0 and 1. Okay? And remember what I said was that this is kind of like the number of particles. So it should be intuitive that this should be kind of like proportional to the how much mass we have in that node, or the density, right? Because we have a grid like this, we have a grid, and we know how many, more or less, how many particles there are. We just need to scale it. So one of the concepts that we're going to be talking about is the density of that node at some time. And that's just going to be some scaling factor, and then it's going to be the sum of all the distributions. And this is a concept taken from statistical mechanics. So I know that none of you have had statistical mechanics or anything like that, but if you're interested in reading up on it, but I feel like this is pretty intuitive, right? That since it has to do with the mass or the number of particles, then, and we know the volume, we just say that there's a unit volume, for example, then this relationship makes sense to some degree. Okay? This is going to be a function of x, t. So, something you need to consider for later. And now we're going to get to the idea of streaming and collisions. So, when a particle moves from here to here, we say that the distribution, right, in this direction is going to be taken from here and just simply put here. That's this part. Okay? So we have the distribution at the neighboring point going to be the distribution in the previous point in that direction. And here, just to specify, this E is the unit velocity, or the lattice velocity, to take you from one lattice point to the next point in that direction. So when you multiply it by delta t, you're just going to get to the next lattice point. And then we're going to have some collision law. And this is not going to be as simple as the lattice gas case, but it can be derived to give you conservation of energy and conservation of momentum. But for now, we can just kind of think of this collision part as the first order approximation of the change in distribution with respect to time. So how will we do that? We take the distribution at this time, subtract it by some value. This we have to calculate through some method and divide it by time, delta t. So this tau is some sort of a characteristic time, and this equilibrium distribution function, f eq, it's kind of complicated, and getting to deriving that, I'm not going to do. And if you want, you can ask Ifan. He knows more about this part than I do. But it's complicated stuff, very mathematically heavy, but it turns out to be a pretty simple equation. So let's see if I have it here. Yeah. So this is the equation. But the things we need to calculate it is the density and some velocity u. And the velocity u is the macroscopic fluid velocity. So we're saying that we have 8 directions plus standing still. And all of those have some velocities. But if we sum those up, as we're doing here, in this way, then we can get the velocity of the fluid at that point. So I realize that these are kind of just equations that you're being given. But deriving them and doing all this stuff is I think is quite beyond the scope of this course. So I'm not sure if it's worthwhile doing. However, on this slide, there's a lot of text, and basically it's all the information you need to make a very simple Lattice Boltzmann equation or a Lattice Boltzmann model. You're told what the density is defined as. You're explained how the macroscopic velocity is defined, and you're given the evolution in time and how that can be calculated. So if we know the distribution function at some time, we can calculate the density and the macroscopic velocities. And based off of those two, we can calculate the equilibrium distribution function, which I haven't really told you what is. But that will basically give you the next time step for the distribution. And that's all you need. Then you know the next time step, and you can keep going and going and going. So why would you, want to implement? So why would you want to use this, humbug stuff that I'm talking about? Just giving you some equations, right? And they're not, very simple, but the result of this is that you get a solution to Navier-Stokes equation for incompressible fluid. And trying to simulate that using a finite difference scheme, it's very hard. If you have a shock, like you would have in an incompressible fluid, shock front, like when you're at home and you have the sink and you close it fast, you can feel this dunk, a water hammer. You get the shock front. That is very hard to compute using a finite difference scheme because of the way we derive it. You're going to get this diffusion numerical. But here, that's kind of taken care of. We get the compressibility in there, and everything is fine. So it's a very simple method to implement. Okay? And I just like to show some of the animations that Ifan made. And yeah, I don't know how much of this makes sense for you guys, but at least we can see a couple of animations. I started the lecture by talking about the flow around the cylinder. And here's an example of that. So we have an initialization. This is just noise to begin with. And now it's stable. And what we're plotting is the densities. Here's the cylinder, the pressures, or the density. Oh, sorry, the velocity field. Yeah, because here it's you have the what's it called in fluid dynamics? You guys had fluid dynamics earlier. So you basically have no flow in the nose here, and so you have the velocity for each of the nodes, the macroscopic velocity that I talked about, and what you see behind here is actually an artifact of turbulence. So you get these eddies that I showed in the plot in the beginning. And it takes a while. It looks like it's stable, but then the way that you've implemented the code is that you have these fluctuations, small fluctuations, so that this becomes more and more unstable, the flow, and this builds, and then you get the eddies. So this is kind of a low Reynolds number. And here it's a bit higher velocity, right? Higher Reynolds number, yeah. It's lower viscosity, yeah. So you get more of these. You get the eddies earlier, and you also get more drastic eddies. And one thing I'd like to ask you while you're, it looks like there's some numerical dispersion or like some numerical instabilities here. Yeah. Mm-hmm. Yeah. But the point is that with a simulation model that he's made in less than half a year. How long have you been working on it? Yeah, 2 months. He's able to not only simulate compressible flow, but compressible turbulent flow. And I'm pretty sure it would take a bit longer to do this in finite difference because you have this massive Navier-Stokes. Yeah. So let's see. I have a couple other animations. This is more like a choke situation where you just, a very simple choke where you have a restriction here. And you see your velocity increases here. And then for some reason you get this split, which I'm not quite sure how or why you're getting. Yep. Yeah, that's the first things that I thought to do as well. A double split. We talked about it, but a double split experiment like this. Okay, and then the last one. This was what I did in the lattice gas simulation, and here you see what it looks like in the Lattice Boltzmann simulation by Ifan. And you see there's a lot more detail, but you have some of the same features. You have the empty space here, a little bit of stuff happening here, but this is, you would never be able to simulate it using the lattice gas cellular autonoma. I actually thought this was really, really neat because you get the very unstable tail. And you could imagine if you're flowing in a turbine, for example, and you have your rotors, then this type of simulation, if you just shift this a little bit, it would show you how the fluid flows in a turbine for slit. And that's a big research area for a lot of production engineers. And so kind of just the practical use of this model. Yeah. We don't have too much time left. Kind of a bit rushed on the last part. Maybe, feel like it's just another equation for you guys to memorize. But if you have any questions about the model or about, implementing it, and you can talk to me or you can ask now if there was anything that was very unclear. Yes. So it's compressible fluid flow for like the simulations you've done has been for around the cylinder. But what we want to try to do is two-phase flow in a micromodel that we do on the third floor. So there's a lot of research stuff going on, and if you're interested in simulation, then I would recommend either talking to Ifan or Carl Fredrik or myself. And yeah. Any questions? You guys want to have a get out of here? No. Yes.